Okay, hello everybody. Today we will continue our discussion with the parsing, but this time we are going to look at this concept of statistical parsing. Statistical parsing with the context-free grammars is very similar to what we did with the CKY parsing or the early parsing, but this time we will include the probabilities of parse trees, and this way we are gonna have a way of resolving ambiguities, parsing ambiguities up to a degree. We are not still saying that we solved the ambiguity problem with the parse trees. We are gonna say that at least these parses are more probable, these parses are not that probable, etc. That's the beauty of the probability, because it will never say that this is not possible. It will say that this is more possible than the other one, etc. So it's going to be a good input for ambiguity resolution of the parse trees. Again, we are not arguing that we will solve these parsing ambiguity problem. Okay. Again, it uses a probabilistic model, and with the probabilistic model we assign probabilities to each parse tree. We may have more than one parse tree for a given sentence, and again, this is going to be a very good base for resolving the syntactic ambiguity. And where do we get these probabilities, the initial probabilities? We are going to talk about it. And the tree sets that are formed, provided by the human linguists, will be the main source of this supervised learning of parsers. And we will talk about having these kind of parse trees, annotated text, how it is useful for producing the grammar of a language, also how they are useful for producing probabilities for the sentences, and we will see those. Okay, so let's look at this idea of probabilistic context-free grammar. Remember the context-free grammar that we looked at last week and the week before that? We said that the Chomsky hierarchy say that at some level there are context-free grammars, at some level there are context-sensitive grammars, at some levels there are regular grammars, and we are going to modify these context-free grammars without going into context-sensitive grammars by the probabilities. Each rule will have a probability assigned. Okay, so we are gonna modify each rule by assigning a probability. Where do those probabilities come from? They will come from our training sets. Okay, they will come from our training set. When we do the parsing with the probabilistic context-free grammars, okay, we will handle each constituency formation with the new probability assigned probability value. So it's not going to be that difficult actually. Once you know the context-free grammars, assigning the probabilities and doing it is not a big problem. Here is an example for a probabilistic context-free grammar. Okay, so the grammar is very similar to context-free grammar. It is almost the same. The only thing is, for each rule there is a probability assigned. As you see, remember the main form of the context-free grammars. It has to be a some value. This gamma could be any combination of terminals and non-terminals. On the left, it has to be only non-terminal, right? It has to be only non-terminal. So for a given non-terminal on the left, all the probabilities assigned to that non-terminal rule has to add up. They all have to add up to 1.0. As you see on the left, I have this non-terminal S. I have 3 S rules. Okay. If I add these 3 up, I got 1.0. Okay. The same thing for the NP. I got 1.0. The same thing for the nominal noun. It goes like that. And for the determiner, I have only these determiners. Okay. So that's basically it. Of course, for the PP, since I have only one rule, what I can say is that rule has a probability of 1.0 application. Of course, by themselves, they don't make much sense, because what do I mean by this? This rule has the chance of being applicable for 1.0 of all the time. Well, if you put this in a bottom-up parser, these numbers will make more sense. And in a few minutes, we are gonna see how these numbers are used. Later, then we are gonna look at how we get these numbers. Okay, how we get these numbers. Good. So that's basically what the probabilistic context-free grammar is. Basically, it's a context-free grammar with probabilities assigned for each rule. Here is one example. The sentence is, book the flight through Houston. Book the flight through Houston. And for each edge in the tree, proper noun Houston, here proper noun Houston 0.8. 0.8 comes from there. Noun phrase proper noun 0.2. Noun phrase proper noun 0.2. It comes from there, right? And yes, let's look at this one. Noun phrase determiner nominal 0.6. Noun phrase determiner nominal 0.6. As you see the idea. So each edge.
Professor, we cannot see the slides now.
What happened to the slides?
Yes.
Do you see it now?
Press the slide.
Do you see it now?
Yes, we can see it now.
I don't know. There is a internet connection problem with the university today. So if there is a problem, just use your microphone. Speak up. Okay. So for each rule application, we have a probability, and I put all these probabilities together and multiply them together. That will give me this 0.1 is here, right? And then 0.5 is here. And then this 0.5 is this one. It goes like that, okay? So multiply each of them, and I will get the probability of derivation, okay? So of course, this one assumes that the production for each rule are chosen independently, which is not a very good assumption, which is not a very solid assumption. But this is kind of give you an idea how we can calculate the sentence probability. We had a way of assigning probabilities to sentences through the n-grams. Remember the statistical modeling of the English or Turkish using the n-grams. Okay, this is another way of assigning a probability to a sentence. But this time we are doing this assignment. Okay, we are doing this assignment in a syntactically unambiguous way. Why do I say this? Because this sentence D1 might have other parsers. This is only a probability assignment for this parse. Previously, when we do the n-gram probability assignment for a sentence, we did not care about the different syntactic parsers of a sentence. Okay, so this kind of solves more problem. It both assigns a probability to a sentence, but it cares about the syntactic ambiguity. Previously, we didn't care about the syntax at all, okay? It was all statistics of the counts of the n-grams. Okay, so that's the difference. Okay, and this is another parse tree for the same sentence. Okay, booked a flight through Houston. Okay, booked a flight through Houston. Through Houston is the PP of this VP. In this case, through Houston is PP of this nominal. This is part of the noun. This is kind of modifying this verb. So these are two different meanings. Same sentence, two different meanings. So this one has 1, 2, 3, 4, 1, 4 zeros and 1, and this one has 4 zeros and 2. So this one has twice the probability of the D2. So I would say P D1 is greater than P D2. Okay, so that's a very good conclusion actually. Why? Because now we have a way of saying both of these sentences are possible, but one of them has a better probability. So depending on what? Depending on my training, depending on my training set. Okay, depending on my training set. Okay, so syntactic disambiguity could help us, probabilities could help us to achieve this syntactic disambiguation. And if you don't care about the meaning of the sentence, or if you don't care about the parsing of the sentence, what we can do is get all the sentence parse trees for the same tree and add their probabilities up. So this is the probability of this sentence irrespective of its parse tree. Okay, I know that this sentence is parsable. I have parsed it in 2, 3, 4, 5 different ways. Doesn't matter. And now I like to assign a probability to this sentence with no regard to its parse trees. Okay, this is sentence probability. This is more like the n-gram sentence probability that we have assigned before. But again, this is more specific. Why? I know that this sentence is parsable. I know that there is at least one tree assigned for this sentence. With the n-grams, I didn't have such a thing. With the n-grams, even if the sentence is a stupid sentence, okay, I can still assign a probability because, as you know, by the idea of using smoothing, we can assign very small probabilities even to nonsense sentences. This will not happen with the probabilistic grammars. Why? Because I have to parse it first. Okay, good. Okay, so 3 useful probabilistic context-free grammar tasks. We are going to look at some of them. Okay, one is observation likelihood. Okay, to classify and order sentences. The second one is to determine the most likely parse tree for a sentence. Okay, this is what we did. And the third one is this one. Okay, I like to form a grammar. Okay, I like to find a grammar. Okay, for a given tree set, and I like to assign probabilities for each rule. Okay, these are 3 different tasks that people usually work with when they deal with the probabilistic context-free grammars. Okay, so we are gonna look at them maybe one by one. Okay, and the most likely derivation, which means that I am going to produce a parse tree with a probability value, and it is going to tell me that although you can produce this parse tree, more than this one is more likely. Okay, you understand this, right? Can somebody translate this into Turkish? John liked the dog in the pen. Pen means kulübe. Köpek kulübesi, kind of. John liked the dog in the pen, and John liked the dog in the pen. Translate this into Turkish, this one. Which is not the right parse tree for this sentence actually.
John kulübenin içindeki köpeği sevdi.
John kulübenin içindeki köpeği sevdi is a translation for this one. The dog in the pen, kulübedeki köpek. John kulübedeki köpeği sevdi. How about this one? John is in the pen, and he likes the dog while he is in the pen. So the dog is not in the pen, okay? John is in the pen. Kulübede köpeği sevdi. So these are two different things. So we like to be able to come up with a parse tree, two parse trees. Both of them are okay, but this one has a higher chances of getting this. Most likely derivation is the first, okay, the second task that we do with probabilistic context-free grammars. Okay, so we are gonna remember our CKY parser that we have learned last time. Okay, so we are gonna modify the CKY parser to parse the probabilistic context-free grammars. But with the probabilistic context-free grammars, now we have the probabilities assigned. So we should modify our parser so that it can handle the probabilities. So what are we going to do? We are going to do this. In each cell, remember, we hold the applicable constituents or the formed constituents for that cell between the words I and J, right? Covering the words between I and J. Now we are gonna put one more thing. We are gonna add, okay, we are gonna add the probability associated with that constituent. If I have a constituent in that cell, what is the probability of it? Okay, and when we are filling in a new cell, we should come up with a way of calculating the probability of the constituents of that cell. That's what we are gonna do. Okay, and the second thing is this. Remember, CKY parser needs the context-free grammar in a specific format. What format is that? CKY parser says that, okay, I can parse the sentences with context-free grammars, but that context-free grammar has to be in some kind of format. What was the format of the context-free grammar for the CKY parser?
It has to be epsilon premium has to have binary rules.
Yes, it has to have the binary rules, epsilon free binary rules. So what do you mean by that? It has to be either A, B, C, or like that. And on top of it, now we are saying that it's going to be probabilistic. So it's going to be like this, and it will have probabilities for each one. So let's see how we can do that. On the left, we have a probabilistic context-free grammar. It is not binary. It's not Chomsky normal form. Okay. On the right, we knew how to make it binary or Chomsky normal form, CNF form. Now I need to come up with a way of assigning probabilities for the new rules that I had to develop. What was the rule? Okay, for the context-free grammar, take all the S's on the left. They all have to add up to 1.0, and all the MPs and all the nominals, as you see. So if I add a new rule here, x1 rule, see, since I am using x1 only once, and there is nothing else, that means that this auxiliary NP thing is 1.0. So that's good. But this S is happening how many times? How many times S is happening? It is happening 1, 2, 3, 4, 5, 6, 7 times. So if I add them together, it has to add up to 1.0. Okay, so let's look at these numbers. This one, and this one. Where do they come from? 0.01. Where 0.01? Where does it come from? Okay, this one did not change, no problem. This one says that I am 0.1. Why? Because it is x1 VP and VP. Okay, I did not change this one. But this one VP, I have to divide that into many parts. Why? Because this VP goes to verb and verb MP and VP PP. So this one and this one, 0.5 and 0.3 here. And since this one was 0.1 and I took this rule because it is not binary, I had to multiply this 0.1 with these two. So I got this now, right? No problem. Okay. How about this one, VP verb? So I need to multiply this one with this one, but this is again another binary rule. And I need to go to the verb rules. Where are the verb rules? Verb rules are, let me go to verb rules, are here, okay? So it is 0.5, 0.2, and 0.3, 5, 2, 3. Okay, so here 0.5 times 0.1 times 0.2. Okay, so I will end up with 0.01. So this is how you calculate the probabilities for your new rules. Okay, and if you add them up, all of them together, for S rule, it should add up to 1.0. And I'm going to do the same thing for the MPs and everything. Okay, so now I have the Chomsky normal form for this rule set. I can do my CKY parsing like before. And let's look at this same sentence. Book the flight to Houston. Again. Book the flight to Houston. So what is applicable for this book? Of course, book is noun, book is verb. And from noun to nominal. Okay. That's I know. From verb to verb phrase and verb phrase to sentence. Okay. So book, noun, book, noun. Where is my noun book? This is verb phrase only. Okay, this is nominal book. Nominal noun. It looks like I don't have the values for the noun, but I don't want to go back to the original slide again. It looks like I had a rule like noun book, and its probability is 0.1. I have that one. Nominal book 0.3. Nominal book 0.3. 0.03 is here. I put it in there, and all the applicable rules. Okay. Then from verb. Okay, I think book verb. Where is verb? Okay, verb phrase book 0.1. I think it is here. Verb phrase book is 0.1. And how about this sentence? How about this one? S 0.01. VP is this one. S 0.01. SVP 0.01. I don't have SVP because this has to be binary, but I have, I guess, S2 book, I guess. Yeah, okay, this is this one. Yeah, okay, we found it. It is direct one. Okay, 0.01. So I put all of them in the book box. So the position 0, 1, 2, 3, 4, 5. Between 0 to 1 book, I came up with all the constituents: noun terminal, noun, nominal, verb phrase, and sentence. And for each one, I have the probabilities assigned. And I am doing the same thing with the second one. Remember the algorithm? Algorithm is like go from left to right. And for each column, go up. Okay. It was like this. So first column I am done. Second column, I did that. This is the determiner and the probability is 0.6. And I don't have anything here because between 0 and 2, I cannot find any rule that says S determiner, VP determiner, verb determiner. I don't find any rules that says A something determiner. I don't have such a rule. So if I don't have such a rule, then I cannot put anything in there. How about this one? Flight. Flight could be noun and nominal, both of them. I am fed in. When I come here, determiner nominal or determiner noun, it will do something. How about these numbers? Let's try to figure these out. NP 0606 015. Okay, this is determiner nominal. What is this? 0.6 here. Okay. Try to figure out 0.6 is this 0.6. And 0.15 is this 0.15. How about this 0.6 here? Where does this come from? Can somebody tell me where does this come from? The rule is this. Rule is NP determiner, no, nominal, determiner and nominal. Rule is this. Can you tell me where that blue 0.6 come from? I cannot read your chat messages because for some reason my Teams doesn't work properly nowadays. Where does 0.6 come from?
Is it the probability of the noun phrase?
It is the probability of the noun phrase rule. You mean this rule? Yeah, let's go to that one. NP, determiner nominal. NP, yeah, exactly, here. Okay, it is NP, determiner nominal. Okay, so that was the rule, right? What was the rule? For each edge, for each rule applied, we put them together and we multiply them. So this is the result of multiplication of these three numbers. Okay, the probability of this one, probability of this one, and probability of applying this rule. And there is a 0.054 chance that I am assigning a NP for between these two positions, the flight between 1 and 3. And we continue like that until we find many S's or a single S or maybe 0 S's in the top right corner of this table, dynamic programming table. That's what we do. So this is a basic step of the probabilistic CKY parser. It is very similar to CKY. I don't add any order of magnitude complicated rules. Okay, all we are doing is just applying CKY rules, doing some multiplication at the end. Okay, and at the end when we have the S's, we will have the probabilities for each. Again, this VP is applied that way. Okay, it looks like this 0.5 is this one, the green 0.54 here, and the blue 0.5 comes from the VP verb and P. I guess it's probability is 0.5. Okay, so it's the book to flight. And after the book to flight, I guess there should be a sentence, right? As I think there should be a okay, there should be an S verb and P. Okay, and I should have it in their book to flight. Do I have it in my? Yeah, okay, I have it. Yeah. So again, this green stuff is here. Green stuff is here. Green, red. What happened to my green here? And blue is from the rule. Okay, continue this way. This true is preposition and these are all empty. For the last one, again I started here, I found the PP prepositional phrase and go all the way up to the corner. Here I have a sentence. Okay, verb noun phrase. Move to flight to Houston. That's one sentence and its probability is this. And the second one is book to flight to Houston. Its probability is this one. So CKY parser only modified, and we are coming up with this nice probability assigned parse tree. And one idea of resolving the ambiguity is taking the most probable parses all the time and not continuing with the different parses with each step. Okay, so the observation likelihood is this. Okay, which one? The dog big barks or big dog barks. So what you do is you run the contextual grammar with probabilities, and whichever has the higher probability will get assigned, will get chosen as the right parse. Okay. So I'm going to skip this one, and we will pick the right one, whichever is. Okay. So we already did that before. I mean, just add all the probabilities to come up with the probability of that sentence, not the probability of the parse tree. We talked about it. Okay, so at the beginning we talked about tree banks. Okay. Let's say somebody went, some human linguists, PhDs in linguistics, okay, they took many sentences. Okay, they took many sentences, and they assigned these probability trees for each sentence, and they gave us this tree bank for us. Okay, so note that when they did this, they did not have any full grammars. So what they do is they start from bottom, they go to up, and they say that when I see this, it's a propositional phrase. Then I see this a noun phrase. When I connect these three, it makes a verb phrase. At the end, there is a sentence. So in a way that without knowing the grammar, they know how the constituency is working. Okay, from the constituencies, they work their ways up to the top. That's what they do. Okay, so our task could be coming up with a context-free grammar with the probabilities, probabilistic context-free grammar. Okay, this is kind of supervised training. Why? Because I have only the trees. Okay, I have only the trees. I don't know the grammar itself, and I don't know the probabilities for the grammar. You might say that, how come you can form these trees without knowing the grammar? Okay, all I'm saying is that when you look at a sentence like this, okay, you don't need to know the whole grammar. You know the constituencies, right? You know the constituencies. When you see a noun phrase or the propositional phrase or the verb phrase, you would immediately know that, okay, this is a propositional phrase. Okay, but for example, a grammar and its parameters. It's a noun phrase, I know that, okay? This is a grammar and its parameters. It's a noun phrase, I know that. Can be estimated directly from counts, and it's a verb phrase, I know that too. So I can make these kind of assignments, and for each constituency part, I can make other assignments too. That way, I can form the whole parse trees without knowing the whole grammar. I only know parts of it. That's how they are done. How these trees are done. Once I do that, once I have these trees, what I do is, what I get is a set of production rules, can be taken directly from the set of rewrites in the tree bank, and the parameters can be estimated using these simple formulas. So you would say that, how many times did I see alpha as a non-terminal in my tree set, and how many times I have seen this alpha goes to beta, and that will give me the probability for this one. How many times I have seen S in my data set, and how many times S goes to this, how many times S goes to that. So that will give me these probability values. Okay, so that's how I get my production probabilities. That's how I get my production probabilities. Okay. Also, again, these are the rules that are applied by a human linguist for at least one of the trees. Okay, somebody said that, okay, S and PVP. Some other people said S and PVP. Okay, so if it is applied once, that becomes my rule. It becomes my rule, and I will make that part of my grammar.
Can I ask something? Sir?
Sure.
These counts are normalized counts, right?
No, they are not normalized. What do you mean? I mean, normalization is done by these probabilities. Of course, they are between 0 and 1, but these counts are not normalized now.
So the count of alpha, for the rule to be alpha, it should be more than 0, right?
Sure, yeah, sure. Otherwise, I mean, again, let's go there, okay? Let's say I have 100 trees, okay? So what is the count of S? It is 100, okay? And out of this 100, how many of them are S and PVP? If it is 30, then 30 over 100 is the probability for this S and PVP.
So will we normalize the probability function then, if we want to normalize the counts? For example, there can be, I think, 0 probability if there's no counts.
Of course, when there is for example, you cannot have a 0 count for an alpha. Alpha is a non-terminal, right? And number of the non-terminals are already in the trees. It has to happen at least once. Otherwise, it wouldn't be a non-terminal.
Okay.
So I think you are trying to. Are you asking about the smoothing? Maybe is that what you're asking? Smoothing?
Yes.
It's not normalization, but smoothing.
Okay.
Well, I mean, yeah, maybe. If it is smoothing what you are asking, again, we cannot have, if nobody applied a rule that says as, for example, auxiliary VP, something like that. If nobody has applied this before, we take its probability as 0. Yeah, that's true. Some trees are not possible with the context-free grammars. We have to reject them. We have to say, I cannot parse this. But there are no normalization with the count, because we are counting these rules to calculate the probabilities, and probabilities are already normalized between 0 and 1.
Okay. I mean, so there is 0 possibility, right?
Yeah. For some, yeah. I mean, if this could be S auxiliary VP 0.0, but we don't write it because there are many of them like that, okay? Remember our Chomsky normal form rules. It says that sometimes I would say S book, right? How many words are there in English like this? There are 500,000. And I cannot repeat each of these rules one by one, saying that the probability of this one is 0 and 0 and 0 and 0. If it is not in the table, then it is 0. Okay, so I think your question is, when we calculated the n-grams, with the n-gram world, there is no 0, okay? If I did not see an n-gram before in my training set, we don't assign a 0 probability to it. But for the parsing, context-free parsing or any other type of parsing, you cannot. So for some of the trees, you have to assign 0 probability, and you have to say that I cannot parse this.
Okay.
Okay.
What if our tree bank is small?
Yeah, if the tree bank is small, then that's a big problem, because if the tree bank is small, you are going to reject some of the valid sentences in the other world. That's a problem, and we don't have a solution like smoothing that we have used with the n-grams. Okay, with the n-grams, if somebody gets, what is the probability of fast go instead of go fast? Okay, what is the probability of fast go? It will assign a probability. It will say that, okay, it will be 1 point times 10 to the 10 to the minus 10. It's a very, very small probability, but it's a probability. But if you say that just produce me the parse tree for fast go, it will say that I am rejecting this. I cannot go because I will not see anything in here. See, there is no book the. If I have a sentence like book the, I cannot parse it. Its probability is 0. Or book the flight through. See, it is none. It is none. I cannot assign anything because my parse tree will not be suitable for that. If there is a number here, then I should be able to produce a parse tree for it, but I don't see it. So your question is basically, we have smoothing, and even though we have never seen that n-gram before in our lives, in our training sets, we could still assign probabilities to it with the n-gram world. But with the context-free grammars, we cannot do the same. Yeah, that's true.
Yeah, that was my question, basically.
Okay, good. Okay, good. So, so maximum likelihood training is something like that. Given a set of sentences, we induce a, but note that I am saying the same thing over and over again. We don't start with a grammar. Okay, we are given a set of sentences. Okay, we induce a grammar that maximizes the probability that this data was generated from this grammar. Okay, and we of course assume that the number of non-terminals in the grammar is specified. You don't get to produce non-terminals. Okay, so it looks like I am out of time for the first part of the lecture. Are there any questions? I can take the questions right now, or maybe I will take the questions after we come back. Let's come back around 14:33. Okay. I will skip a few things. We like probabilistic context-free grammars, but we said that they assign probabilities to parse trees, and whichever has the higher probability, maybe we can choose them. But they have some problems, because when we look at the probabilities like this, okay, this one doesn't tell you anything about the words being used or the context. Okay, it says that if you have a noun phrase, it is most probably it's a determiner and a noun. Okay, it's something like that, and less probable it is noun phrase and the prepositional phrase. But they say that this decision should be dependent on the words being used. Okay, the words being used. So what do I mean by this? For example, when we say I ate, okay, I ate my lettuce with fork. Okay, so ate with fork, right? This one is ate with fork. How about this one? I ate my lettuce. Lettuce is lettuce. What is lettuce? That is marul with meatballs. Okay, so this lettuce with meatballs, okay, this is the noun phrase. My lettuce with meatballs is noun phrase. Here, my lettuce is the noun phrase, right? So what is the difference between these? The difference is the fork or meatballs, right? So I should, when I see the fork, with fork, when I see this with fork, okay, I should be able to give more probability to noun phrase, propositional phrase sentence structure. Okay, when I see with meatballs, I should give more probability to noun phrase. But the rules that I am using right now is not, with the rules that I am using right now, this is not possible, because these rules, they don't consider any verbs or the nouns, their context. They say that using this sentence rule is 90%, this is 10%. So they say that maybe we can change this, maybe we can find lexicalized probabilistic context-free grammars. So what do we mean by that? We will have rules, they are specialized to specific words. For example, for eating verb phrase, okay, for ate VP, there is a specific rule, and for run VP there is another specific rule, and I can change these rules. Okay, so another example. John put the dog in the pen. Okay, this is not the correct parse, because this kind of looks weird. I mean, just the dog is in the pan, not John is in the pan. Okay, so with the probabilistic context-free grammar, I should be able to say that this is not the correct parse. Okay, this is not the correct parse. The correct parse is this one. Okay, for that one, again, as I said before, we are gonna have parse trees like this, and we kind of talk about this when we discussed the morphology, and we said that for some of the rules it doesn't work like that way. For some of the words and for some of the derivation rules, they are not applicable. For example, what did I clueable? Clue and clueable doesn't work. This run and runnable works, but clue and clueable doesn't work, right? So this able suffix will work for some of the words and it will not work for some of the words. It's like something like that, okay? Like thing, okay, like verb, VBD, like verb, sentence, okay, this John and MP. So each constituent has a head verb, and for each head of the rule, we will assign a different probability. So we can have this kind of lexicalized production, and each rule will have its own probability. Of course, for this kind of context-free grammar rule set, we will need lots of training data, and getting that training data is not going to be very easy. But I'm just giving you some kind of a solution. Okay. So let me skip some. Collins Parser is kind of trying to deal with these kind of problems. We don't have that many parameters. We don't have that many training sentences, but we need to solve these problems. I am not going to go into this parser, and I will skip this part, but I will talk about one interesting stuff, which is human parsing. Okay, human parsing to some level is similar to our bottom-up sentence parsers, but human psychology is a little bit different. There is a field named Psycholinguistics. Okay, Psycholinguistics. Okay, and we can, by studying the human behavior when they see the sentences, we can build parsers that behave like human parsing, human psychology. Okay, so for some applications, we can predict the human reading time as measured by the tracking the time taken to read each word in a sentence. Okay, so these psycholinguistic people, they set up experiments and to show how these reading times are changing. Okay, they say that, okay, the words that are more probable given the preceding lexical and syntactic context are read faster. Okay, if the word is more probable, then those words are read faster because you anticipate the word because those are more probable. Okay, so look at these three things. John put the dog in the pan with a lock. Okay, and John put the dog in the pan with a bone in the car. John liked the dog in the pan with a bone. When you look at those red words, some of them are easy to read, some of them are not that easy to understand and read. Okay, these are coming from the psycholinguistic things going on in our heads. Okay, so and again, as humans, we don't read the whole sentence and parse it when we see the dot. Okay, we do it incrementally. Okay, we start immediately parsing. John put the dog in the pen. Okay, we start parsing the sentence when we start reading it. When the sentence is complete, usually the parse tree that we have formed in our head is the right one. If it is not the right one, then we have to go back and we have to reread the sentence and we have to think about it. This doesn't make any sense. And as humans, we don't like these kind of situations. We like to be able to read the whole sentence, and when we are done reading the sentence, the tree that we have formed in our mind should match the sentence. Okay, so that's what we like. That's how we work efficiently, and our parsing is done incrementally. We don't like garden path sentences. We are confused by them. Okay, we are confused by them. For example, read this one. Read this one. Okay. The horse raced past the barn fell. The horse raced past the barn fell. Doesn't make sense at the beginning, but when you say that, okay, the horse raced past the barn is the noun phrase. This is the noun phrase, and this is the verb phrase. Now it makes sense. But usually when we start parsing it, when we start reading the sentence, we say that the horse is the noun phrase, race past the barn, okay, is the verb phrase. What is fell then? But that doesn't make sense. But so we have to come back and we have to reform our parse tree. How about this one? The complex houses marry students. This is kind of different, but at first I think that the complex houses is the noun phrase, married students is the verb phrase, but doesn't make any sense. Houses don't marry students. So what is the noun phrase? The complex is the noun phrase. Houses marry students is the verb phrase. Okay. Again, the old man. It look like the old man is the most pro. The old man is a noun phrase, right? The old man. Where is the verb? The verb is there. The old is the noun phrase. Again, these are garden path sentences. Okay. And incremental computational parsers they have difficult time doing the parsing for these kind of sentences, but they are very efficient. As humans, our parsers are very efficient. But if we do it incrementally, when we start doing without reading the whole sentence, okay, without reading the whole sentence, when we start parsing these sentences, we may end up in a garden path with no end, with no solution. So we need to back up. Okay, we need to backtrack and start parsing again. Find the verb. Where is the verb? Verb is here. Okay, something like that. Okay, good.
Can I ask a question, sir?
Sure.
In the previous slides, we saw a problem about, like, for example, there was VP8. The problem was we didn't know the specific phrase, so we included, for example, VP8 rule, right?
Yeah. Mm-hmm.
So is it just for that word, that 8, or isn't this like a workaround rather than a solution? Because
yeah, well, the solution for that problem was, I mean, when we say it's a possible solution for that problem, we shouldn't say the solution, is to lexicalize rules. So we don't say all the verbs are going to behave this way, but we say that the verb for eating, if you are doing it verb with anything, okay, maybe the probability of you applying this rule is better than the probability of applying that rule. But for the verb put, it is maybe just the opposite. Maybe the probability is low. So they say that change your probabilities depending on the verbs being used, or the head of the verb actually, not just the verb, head of the whole sentence, or head of the constituency. That was the solution proposed, but the problem for that one is you need lots of data to come up with probabilities for each verb or noun or that kind of stuff.
Yeah, I was gonna ask that because for every word, like we can do it maybe, for example, if we take, for example, 8 and maybe put it in the same set as drank.
Yeah.
Okay, I was just gonna.
Yeah, so I mean, I'm not offering any solutions for you, and that's a problem. Well, I mean, I went into that topic saying that probabilistic parsers are good, but they have some serious problems. And remember when we argued at the beginning that they are good for resolving the ambiguity. I mean, as they are not going to solve all the problems that we have. Ambiguity will not be resolved, and sometimes if you don't use the lexicalized rules, you are going to resolve ambiguity in a wrong way if you don't have the lexicalized stuff. So without looking at your words, what kind of words and the context, it is not easy to assign a probability that will be helpful for the ambiguity resolution. That was the whole idea of those slides.
Okay, thank you.
Okay, thank you. So the garden path sentences, we like these kind of parse trees. Parse trees that kind of resolve everything just incrementally. This looks weird, right? I don't want to see very large noun phrase at the beginning of the sentence. The horse raced, especially when you say it's raced, okay? You immediately think that this is a verb, okay? Yeah, this is part of the main verb phrase of the whole sentence. But at the end, this doesn't make any sense. You need to go back. This is how the human parsing works. And why are we studying this? We are studying this because usually they tell you not to construct sentences like this. The horse raced past the barn fell. Okay, it is difficult to read these kind of sentences. Similarly, the center embedding is talking about the same thing. Okay, the cat chase died. We can kind of understand it. Okay, the cat chase died. Okay, humans are good enough to they are smart enough, or they have the memory. Their memories are large enough to handle this kind of level of nesting. Okay, but how about this one? The rat, the cat, the dog bit, chase, died. Okay, the dog bit the cat chased the rat died, right? That's what the sentence says. How about this one? The rat, the cat, the dog, the boy, on, bit, chase, died. This one doesn't make any sense. I mean, grammar-wise, maybe for the English grammar it is okay. Maybe this one is okay too, but we don't prefer these kind of sentences. This is like recursion, right? And our head is good for 1 or 2 levels of recursion, but if you do more than that, doesn't make much sense. Instead, we prefer these kind of sentences. The boy owned a dog that beat a cat that chased a rat that died. This looks like a tail recursion. Remember tail recursion? What was the definition of tail recursion? A tail recursive function is a function that what?
doesn't branch.
No, it's not. Oh no. Tail recursion does what? What is tail recursion? It's a recursive function, but in that function, the last executable statement is another recursion. Okay, so you don't do your recursion in the middle of your function. It is the last thing. So this is center embedding. Our recursion is happening in the middle of the sentence. This one, no. The boy owned a dog that I am specifying I am giving more information about dog. Beat a cat that, now the cat, now the chase, okay, now the rat, etc. So this is tail embedding and it works much better for the humans. Okay, I think that's it for the context-free grammar parsing and the statistical or the probabilistic context-free grammars. If you don't have any questions, I will start talking about dependency grammars. Are there any questions about the context-free grammars? By the way, I only talk about the probabilistic context-free grammars for the CKY parsing. The early parsing that uses the top-down parsing, of course, those rules are still applicable there. With the early parsing, with the top-down parsing, you can calculate the probabilities for the sentences. That's possible too. I'm not going to go into there anymore. Okay, it looks like there are no questions. Let's talk about the dependency grammars. But for these dependency grammars, I will use some other slide set from Manning. I modified some of his slides. Okay, so when we talk about parsing, most of the time we talked about context-free grammars. Okay, with the context-free grammars, of course, we start with the words, but we start putting the words together to make more complicated structures. These are the words: the cat, cuddly, by door. Then when you say the cuddly cat, it's a noun phrase. Okay, by the door, again, into phrases. Then we combine the phrases. The cuddly cat by the door makes a more complex constituency, and we can use this, the cuddly cat by the door, as a noun phrase for a whole sentence. That's what the main idea of the context-free grammars, how the words come together, and can we explain this using these kind of rules. And we said that yes, it works. Context-free grammar is this. Okay, why do we need this? Because the idea of parsing is interesting. It tells us the structure of the sentence, okay, to be able to calculate or to interpret the language correctly. Okay, and the humans communicate by putting the words together and forming these kind of groupings. Okay, so we need to assign sentence structure to given sentences. That was the reason. So we talked about this last time, I guess. Okay, but when you do that, it is not that easy to assign a single meaning to a sentence. Many things can happen. That what we call is ambiguity. Okay, and we talk about this. Okay, this is interesting. Do you understand this sentence? Mutilated body washes up on Rio Beach to be used for Olympics beach volleyball. You understand what is funny, right? Garden pet sentence here. Okay, so far we have only looked at the context-free grammars, and context-free grammars are good for some languages where the word ordering is kind of fixed. But for some languages, context-free grammars doesn't make much sense, okay? Because those languages, they have free word order. You can change the order of the words, okay? The meaning of the sentence changes, but sentence is still a valid sentence. So it doesn't make much sense to have context-free grammars for those kind of languages because everything is parsable. There is a parser for everything. Lots of ambiguities, okay? So they have these dependencies. Dependencies say that there is a relationship between the lexical items. Here is a sentence. Can anybody read the sentence with the dependencies? Okay. Bills on ports and immigration were submitted by Republican Senator Brownback of Kansas. Okay, this is the sentence. So at the top of the sentence, when I parse this sentence using the dependency parser, at the top of the sentence, this is the head, is the verb, and okay, this is the object of the verb, this part, and this is the subject of the verb. So there is relationships between the elements, lexical elements of a sentence. We don't say that these words come together to form this constituency. Instead, by going over this binary relationships between the elements of a sentence, we assign a different structure, dependency structure. It is not constituency structure. Previously we assigned okay, constituency structure, how the words come together next to each other. This one doesn't say, I don't care about the order, okay, I don't care about the order. All I care is the relationship between the lexical elements, binary asymmetric relationships. Okay, so usually we mark them with the types of the relationship. For example, there is submitted and bills. There is this nominal subject. Bills is the nominal subject of this verb submitted, and this is a passive subject. And submitted and verb auxiliary relationship between them, and this is the object. Brownback is the object. Okay, this is modifier, another modifier, nominal modifier. Okay, so the arrows are showing us the relationships, dependencies, and with the arrows, okay, there are types of these relationships. This is what we call is a dependency grammar, and these dependency grammars are actually, they are older than the context-free grammars. People started using them thousands of years ago to explain the word languages, human languages. They are still being used nowadays. They are more common than the context-free grammars because they are more applicable for many types of languages. And if you apply these kind of dependencies to your sentences, you will end up having a tree like this. Okay, there is one head, root, and you go to the end, you reach your leaves, and since it's a tree, okay, it is acyclic. You cannot find a cycle because these dependencies are binary dependencies, and it is asymmetric. What is asymmetric? There is a auxiliary relationship between these two from here to there, but the opposite is not true. Opposite is not true. Okay, as I said before, 5th century BC, they have this Panini's grammar. Okay. The Arab literature, the Arabic scholars, they have used this idea to study the language of Arabic long time ago. In this century, or the previous century, 20th century, in 1940s, this guy, I think we have seen his name many times, and we have seen this name many times. Okay. They played with this idea of context-free grammars, or the grammar hierarchy. Okay, and although at the same time, similar times, this guy, he started looking at the dependencies. Okay, later we started talking about the context-free grammars. Nowadays, as I said before, we are using dependency grammars even more. And dependency grammars are more suitable for languages like Turkish, where the word order is freer than the other languages. Here is one example of dependency grammar assignment, dependency tree assignment for a simple sentence. Discussion of the outstanding issues was completed. Okay, so we make a dummy root. The root is not part of the sentence, of course. The root is not the part of the sentence. Root is connected to, okay, completed is dependent on root. It is the verb of the sentence. Was is the auxiliary. You remember that one? Okay, it is dependent. And discussion is dependent on completed. And what? And issues is dependent on discussion. And again, outstanding is dependent on issues. As I said, it goes that way. So with the dependency grammar, as the name implies, just lists the dependencies in a way that these binary relationships forms a dependency tree. It's not like context grammar kind of assignment tree, but it's a dependency tree. The word order is not important. The word order is not important. With the dependency trees, with the context-free grammar trees, the word order is so important. It was noun phrase, verb phrase. It is not as VP and P. These are two very different things. With the dependency grammars, word order is not important. Okay, I say that wherever this completed goes in the sentence, doesn't matter for me. It is dependent on root. Okay, and everything is possible with the same thing is possible with the other words in the same sentence. There are some other examples here. Of course, with any parse method, tree banks are important. Okay, and this is an example where I show you both the tree and the types of the dependencies. Okay, why is the city called Miramar? Okay, where is the verb is here, so I don't have the root. Let me put root like that. Okay, so with the verb, this is subject here, and other than the subject, this is adverb modifier there. It's a question sentence, that's why it's a little bit different. This is another question. This is not a question. I think Miramar was a famous goat trainer or something. Okay, think is the, again, root goes to think and subject, and this one is dependent on nominal subject. Okay, this is a composition. I compose two things, trainer or something, composition of the two things, and one of these compositions is this one, nominal subject. The other one is this one. Okay. So these types could be different depending on your data set. But as we see here, all we do is explaining binary relationships between the lexical items of a single sentence. Maybe some of you have realized that for some reason, these arcs going from one word to another do not intersect, right? They always have this nice form of this one goes there, and this one also goes there, and this one here and there, and this one is like that, and maybe there, and it's like that, right? Did you realize it? Did you see it? They don't intersect. It doesn't have to be this way all the time, but we like this kind of structure. Because it makes our job a lot easier to write a parser with this kind of structure. And this is called projectivity. Okay? And we will talk about this projectivity later. Sometimes we need non-projective 3 assignments, dependency assignments for some sentences, and we will see examples of them later. Okay, since we are living in a machine learning world, okay, annotated data, if it is available, and it should be useful for many things, and annotated data is available with the dependency grammars, okay, and although at the beginning things might seem a little bit slower with the annotated data, but if you have annotated data, we could do many things with it, okay, including the evaluation of the systems, okay, including the formation of new grammars and etc. Okay, so what do we have as the relationship between two lexical items? What kind of information do we have between them? Okay, it's a good thing to look at actually. When we say two things are dependent on each other, for example, bilexical affinities. What do you mean by bilexical affinities? Two things are related usually. For example, discussion and issues here. Issues and discussion. These two things are related because you usually discuss issues, right? Semantically, they are related. We call them bilexical affinities. The other one is usually things are related to each other when they are close in a sentence. Although we said that these dependencies, they are not using the word order a lot, but the proximity, the distance between words are important really. And dependency distance is going to be important when we say two things are related or dependent on each other. Okay, the intervening material. What do I have between these two? Other than the distance, what do I have between these two? Okay, usually the dependencies do not span over the verbs or punctuation. That is interesting. You don't write arcs over the verbs or the punctuation. You're not going to see anything like it starts here, goes to the other side. Okay, that's a very serious restriction. Okay.
What if it refers to another sentence?
It refers to another sentence? No, it cannot. Most of the time, the grammar, especially I'm going to show you, will not do that. No. I mean, what kind of things, what kind of relationships do we have? Relationship types do we have? We have our compounds, we have our modifiers, determiners, right? Subjects, objects, and that kind of stuff. These are all parts of the same sentence. When you do the compound, it is and or kind of stuff, right? When you say the determiner, these, their, etc., right? When you do the auxiliary, it has to be can, does, etc. When you do the pronoun, it has to be I, you, etc. So it is. I mean, it could be some case, but it is very rare to span over the punctuation end of sentence or span over the main verb of the sentence. Because why is that happening? Because the main verb usually is at the top. The root does that. Okay. So nobody is going to go. Nobody going over the verb. Verb is the root of the whole thing. It grows out of the verb.
But in dialogues, for how do we show the trees? For example, this is a dialogue, and it says, "Why is the city called Miramar?" What if we put this instead of the here? Would be the dependency relationship go to another sentence?
You are talking about co-reference resolution, okay? If somebody says that what happens if I forget my money? Somebody said this. The other one says that I did not think about this. You are saying that this thing is referring to forgetting about the money, right? This is not dependency. This is co-reference resolution. What is this referring to? Forgetting about the money, okay? But this sentence, I didn't think about this, is a sentence by its own, okay? And it depends on this think.
Oh, I see. Yeah.
Okay? So we are talking about not meaning, we are talking about syntax here. We are talking about the grammar, okay? So this sentence is a sentence by itself. To be able to parse this sentence, with some ambiguity of course, I don't need to read the previous sentence. Okay? When I draw this kind of arrows in the dependency parsing world, I am not talking about the co-reference. I don't say this is referring to that or this is referring to this or etc. We are saying that these two lexical elements of this sentence are dependent, and these are the dependency types. And these dependency types are not semantic types, these are syntax types, such as the subject of a verb, object of a verb, conjunction of a noun, modifier of a noun, determiner of a noun, and etc. Okay, so that's a good question. Good. Okay. And we talked about the valence. I think that the last question was about the valency of the ads. Okay, good. Dependency parsing is, of course, is the process of assigning dependencies between word pairs. Okay, word pairs, and the final tree is a tree. Of course, it has to be acyclic. This cannot happen. A is dependent on B. B is dependent on A. This will not happen. And at the top, I have a dummy root. Okay. And this one, as you see, this one is not projective. I will give a talk tomorrow on bootstrapping. So this one is projective. I think the right version is I will give a talk on bootstrapping tomorrow, right? If I see, I like to prevent this one. If I move tomorrow at the end of the sentence, okay, if I move tomorrow at the end of the sentence, then I can prevent this. I can prevent this intersection. I will give a talk on bootstrapping tomorrow. It will work. But sentence is written that way, and in English, I usually accept this kind of sentences too. So this is actually difficult to achieve with the context-free grammars. Context-free grammars are not good with the projective structures. Okay, so I will give a talk tomorrow on bootstrapping. Is not very easily achievable with the context-free grammars, and we will see why in a few minutes. So that's called projectivity. Let's talk about this projectivity in a more detailed way, but before that, let's take some break. When we come back, we will talk about the projectivity, and I will talk about how we use a parser for this dependency structures. Okay, so it's going to be easy, but we are not going to solve all the problems. We will leave lots of stuff out. We will ignore those kind of problems, for example this projectivity, and we will say that maybe this will solve the projectivity that way or this way. Okay, let's take 10 minutes of break. So let's be here
Can I
around.
say something?
You have a question?
Not a question, but I realized that we are not recording in Teams right now.
Really? I think somebody has stopped it. Anyway, I am recording. Let me start recording again. I am recording locally with my OBS, and I will post it on YouTube.
Okay, thank you.
Okay, so 15:33. Okay, so the definition of projectivity, actually we said that there are no crossing dependencies, dependency arcs, when the words are laid out in their linear order, with all arcs about the words. So in this case, this is not a projective tree, because who is doing this? Okay, it is intersecting with two things. Okay, dependencies are parallel to context-free grammar tree, and they must be projective. Whatever you produce with a context-free grammar, it has to be projective. Okay, that's kind of expected, because on the right-hand side of the rules, okay, each constituency is by itself. You cannot break into, for example, when you say A goes to B, C, the constituency B and C are separate. You cannot take anything from C and put it into B. They are two different things. So the constituencies will happen in each other, and between B there will be constituencies in each other. So if your dependencies are parallel to context-free grammar, then you satisfy the projectivity automatically. Okay. The dependency theory normally does allow non-projective structures to account for displaced constituents like this one. But I mean, we like dependency, as we said before. It is easy to write parsers for the projective dependency trees. Okay, so let's look at this dependency parsing. What kind of things that we have? Okay, we have dynamic programming with this complexity n to the 3, n being the number of words. We have graph algorithms. Okay, the graph algorithms, they say that each word is a node of a graph, and my task is to find the tree out of this graph to represent the dependencies. Okay, so it's going to be a tree. So the graph-based algorithms, of course, they can handle this non-projective cases too. And there is this constraint satisfaction-based stuff, and finally, the one that we are gonna look at, this one, transition-based parsing, which is not a very good parser, but it is simple enough to explain. And so we are gonna look at this transition-based parsing. Okay. So let's look at this greedy transition-based parsing. It says that, okay, this one is machine learning based again. So what do we mean by machine learning? At some points we are going to ask question, should I do this or that? Do this or that? Okay, kind of questions. And it will give us answer, you should do this, not that. Okay, so it will be machine learning based stuff. And it is greedy. That means what? It means it's going to find the first parse tree. It's going to find the first parse tree, and we may not find all the parse trees available for that sentence. So let's look at the structure of it. Structure is our parser is basically doing a sequence of bottom-up actions. Three things that we are doing. Okay, we are shifting. Shifting means reading a word from the input. Okay, so that means we are doing it incrementally maybe. So shifting is reading a word. Reducing is assigning a dependency between two lexical items. Okay, between two lexical items. So reducing can be done in two ways. Assign a dependency from left to right or right to left. Okay, so these will be our basic actions: shift, reduce, left, reduce, right. Okay, so if we look at the formal parser, it will have a stack. Okay, we written with top to the right. So if you have a stack sigma, okay, and at the beginning we have root in it as the initial value, and top is to the right of the this stack. So after the root, maybe I will do this I and etc. It will go that way. Okay, so this is stack. So it's going to be, my elements are like B, C, D. The top of the stack is D. Okay, so this is my stack, and it will grow like towards the left. So the top of the stack is on the right, and we have a buffer B, but buffer beta. Okay, buffer beta, its top is to the left. Okay, and beta basically holds my sentence. Okay, book that flight. Okay, so the top is on the left. This is like a queue actually, and it starts with the input sentence. So my input sentence is like that. When we shift, we are gonna read words from this buffer beta. And then I have a set A. Inside this set A, I will have dependencies. For example, I will say root and think, okay, are connected with this dependency type verb. Okay, and this A is going to start with empty. A is going to start with empty, and it has a set of actions. Those actions I will explain it in a few minutes. Okay, so
can I ask a question about machine learning?
Sure. Why I didn't talk about the machine learning part yet, but why not just?
In the previous parts, we saw, for example, we trained parameters like they were the probabilities of each rule, right?
Yeah.
So this is considered machine learning.
Sure. Yes. Any tree set, any data set that we have, and we are learning some parameters out of that training set, can be considered as machine learning. With the probabilistic context-free grammars, yeah, we are using machine learning.
So we could use also deep neural networks too, because we have the parameter and we have the solution.
For the previous example, because I mean, usually with the ultimate machine learning applications, the result, the answer from your machine learning method is your final result. In our previous case, all we are doing is calculating the probability values for the rules, and these don't make much sense by themselves. Okay, they are used in some other algorithm like CKY algorithm, right? So calculating those probabilities using machine learning using neural networks is not a very meaningful thing. But the machine learning stuff that we are going to use for this greedy transition based parsing is going to make more sense. We can use neural architectures or deep learning to help us do this parsing. And in fact, some of the best dependency parsers use that kind of structure.
For greedy transition based parsing, right?
Yes. Okay. So basically, to sum up the answer to your question. Previously, yeah, we used very limited amount of machine learning to calculate those probabilities for the probabilistic context-free grammars. But for this case, for this dependency parsing approach, a greedy transition-based approach, we may use a full-scale machine learning approach. Okay, let's look at these. Okay, stuff. These are the These are the steps of transition-based dependency parser. The notation might look a little bit complicated, but it is not actually. It says that your stack sigma should start with a root. Okay, this is a dummy root. That will be root of the whole tree. And these are our words, W1 to Wn. At the beginning, our arcs are, dependency arcs are, the set of dependency arcs are empty. I have three actions that can happen. And which one is going to be applied? Again, we don't know. It will be decided by the machine learning algorithm. Should I shift? Should I left arc or should I right arc? Okay, these shift, left arc and right arc only tell you what you are doing, okay, how you are doing it. They will not tell you when you should shift, when you should left arc, and when you should do the right arc. Okay, the definition of shifting is this. Definition of shifting is this. Given your three data structures, your sigma, okay, your stack, your buffer beta, and your arcs, okay. If you have your wi at the beginning of this beta buffer, like let's say you have your root as your sigma, and you have your wi, then the rest of the wi plus 1, wi plus 2, etc. And you, let's say as a, you have empty. So this is your beta. Okay, or maybe I should say this is your beta, and this is the first word of your beta. When you do the shift, what you do is you get that wi from the beginning of this buffer and you put that word on top of the stack sigma. So after you shift, this is what you do. Root and then wi, this becomes your new sigma, and wi plus 1, wi plus 2, ... and then your a. So this is your beta and this is your a. This is the meaning of shift. Okay, I still did not tell you when to apply this operator shift. Okay, so let's look at this left arc. Again, the idea is same. If you have a stack like this is your stack, and if you have beta and arc, so that means what? I have two words at the top of my buffer or my stack, wi and wj. After I apply the left arc, the things become like this. Wj will be on top of my stack, beta will not change, but I will add a new dependency. To my dependency list, arc list, by making a new arc. Make a new dependency between wj and wi. Okay, left arc means that there is a dependency between this wj and wi, and add that to the dependency list. Right arc is very similar. Okay, the same, it starts with the same wi, wj. I will do the same thing, but this time I will keep wi on my stack, and I will put this wij relationship in my arc list. So one is putting a left arc, the other one is putting a right arc. So it is like, let's say, these are my words. For this word, one is doing this, the other one is doing that. Left arc and right arc. Okay, so these three operations, apply these three operations in some order. In what order? It depends on your data, and it depends on what your machine learning algorithm says. And at the end, you are done. When you are done, just somebody tell me when this finishes off. When this algorithm finishes off, it will continue until what? It will continue until somebody talk. It will continue until
buffer is exhausted.
all the words are exhausted yet. It will continue until our beta, which is the full sentence, is complete, and my sigma will include, okay, my sigma will include the root word. Okay, that's it. Okay, let's see an example. Actually, I ate fish. These are the rules. Okay, when I started, remember, this is my sigma, this is my stack, this is my beta. Okay, this is my sigma, this is my beta, and when I do the left and right arc thing, I will show them in here. Okay, so at the beginning my A is empty, and my beta, inside my beta I have W1, W2, W3. My root is here. Okay, first my machine learning algorithm looks at this picture. My machine learning algorithm looks at this picture and it says that shift. Okay, I shifted. Shift means that get one word from this buffer and put it at the top of this this stack. So I push that thing I on my stack. So I have root I. And I gave this picture to the machine learning algorithm again. What should I do? Shift, arc left or arc right? It says that, okay, get this one, 8. So I have this. Root I 8. Okay, by the way, how would you do this? Okay, root, at the beginning, what should I do? So tell me the arcs for this one. Tell me the arcs for these 3 words.
All possible arcs.
No, the correct ones. What is the final? What do you expect as your final dependency tree?
At the root 8 and
yeah, the root is like that, and this is our verb, right? And then what?
Then 8 and 5, but I don't know the relationships. Okay.
So this one, you know the relationship. This is so easy. This is the subject and this is the object. Okay, so I am expecting that. Okay, one left shift, one right shift, and one left shift. Oh, sorry, one left arc, right arc, and another left arc. That's what I'm expecting. So there will be 3 arcs at the end of this parsing, and I will shift 3 times. Shift, shift, shift. So I already shifted 2 times. I 8. Now let's see what the machine learning algorithm says. Remember, the machine learning, this left arc and right arc, it only puts arcs between the top 2 elements of the top two elements of the stack sigma. So at the beginning I cannot put any arcs because there is a single element. Now maybe I can put an arc between these two, but I know that root should be connected with the verb of the sentence dependent, so I don't do that. But here something interesting is happening. So I have my root and 8 at the same time. So okay, left arc, it says. Left arc means that I put an arc between I and 8 and I remove I. Okay, so this is what happened. Nominal subject 8 and I put this into my dependency list or dependency arcs. So I have a arc now. So arc is like this, and subject. And after that it says again fish, shift fish. I shifted fish, and when I shifted fish, what happened? My buffer is empty now. My buffer is empty, and my buffer empty doesn't mean that I am not done. I am done. No, because I have to keep I have to keep running this until I get all of my arcs. And this one says that right arc between 8 and fish. So this one was left arc and this one is right arc, and it is object. Okay, another right arc between 8 and root, and 8 and root is here. Another right arc. Okay, two right arcs and one left arc, and I am done. I have this root at in the buffer. So it looks like most of the work is done by this machine learning algorithm. It only knows that when to shift, when to right arc, and when to left arc. So it's as you see, we don't do lots of searching. It is greedy. Why do we say greedy? It makes a decision and it continues on that decision. It doesn't do backtracking. Previously, we didn't do that. We said that this is possible and this is possible, and let's keep that in the table, and let's do that and that and that and that, right? We don't do it that way, okay? That's why this one has the possibility of producing only a single parse tree.
So the parameters we will train is that given this sets arc beta alpha, which decision you will make will be the decision the machine learning algorithm will make.
The machine learning algorithm will give you three things. It will tell you either shift or left arc or right arc. That was the final decision. Okay. Excuse me, I should take this. Efendim? Merhaba Kadir Bey. Teşekkürler. Siz nasılsınız? Yok estağfurullah. Şimdi dersteyim de Kadir Bey, hocalarla konuştum. Ben bugün hazırlamak üzereler. Yarın sabah inşallah size iletmiş oluruz dosyaları. Tabii tarayıp göndeririz biz onları, evet. Görüşmek üzere, iyi çalışmalar. Okay, so the machine learning algorithm will tell you three things. What are the inputs of the machine learning algorithm? The inputs are, okay, this picture. Inputs are this. Inputs are our stack, right? Our word buffers and our dependency arcs. Those are the inputs. So the inputs are complicated. So how do I train this? I train this because I have many dependency trees manually assigned before. I train my machine learning algorithm on this one using those trees. So the output is simple. Output is just one of three. But actually, it is not that. It is not just three. It is more complex because I need to make a decision on this. What is the type of this dependency? Is it subject, object, root, right? So what is the type of it? So output is maybe in general category is three: shift, left shift, or right shift. But under that, under the shift, under the right arc or left arc categories, I need to come up with the dependency type 2.
Does this algorithm ensure we will have a tree that is projective, or will it be a tree?
Ask that again, Salman. I did not understand your question.
Will we have after these decisions of, for example, shift, right arc? Is it ensured that we will have a tree or arcs that is
sure,
projective?
Yeah. Well, this one says that this root is going to be assigned last, right?
So it's projective.
Yeah. So this is going to be projective. Why? Because once we start doing stuff and doing those assignments, I keep them in a stack structure. That stack structure is always going to make sure that whatever I did before will be under my arcs, okay? So this is going to be the final one.
But it's a dummy rule, so there can be...
If you forget about these three, okay, if you forget about these two, so what I am doing is making an assignment to the top of the stack, and later I am forgetting them. There is no way that I can go in them and make an intersecting assignment.
Okay.
That's why this is a simple algorithm that can achieve only projective trees.
For example, when we are putting to the arc a relationship, do we know that the relationship we put in isn't conflicting with the other ones we put before? For example, maybe can it be asymmetric?
You mean by conflicting, you mean intersecting?
No, not projectiveness. By dependency, by the definition of dependency, it should be asymmetric. For example, we can do A to B then B to A, right?
Oh yeah, sure. Well, I mean, once you do a right arc or left arc, you remove one of the elements from your stack, right? So each one there is only one chance to assign a dependency for each of them. So if you like to do A to B, then B to A, then using some kind of a mechanism, you need to either get B or A out of the unused list, which is that we don't have, okay, and make this assignment again. Remember this one, these rules? These rules say that, okay, if you are doing left arc, you're going to remove WI from your stack. If you are doing the right arc, you're going to remove WJ from the stack. Okay? Once they are removed, there is no way I can put them back on my stack. If they are not on my stack, I cannot make any assignments.
Yeah, I see.
Okay? And you might say that in this case, I am keeping my WJ on my stack and I am keeping WI on my stack. What happens if I keep the same word over and over and over again? But that's possible to have lots of dependencies on the same word, right? This is possible. But whenever I do this assignment, I am removing each of these words from my stack. So there is no way I can do anything like that. Okay, good. So Arc standard transition based parser works like that. And although I did not, although the slides did not tell us any much about the machine learning algorithm, Selman asked me lots of questions and about this machine learning algorithm, and I talked about it a lot. So that's a good thing. So we have left to explain how we choose the next action. It is machine learning. We ask the machine learning algorithm, what should I do now? And it's going to tell us what we should do. Okay, that machine learning algorithm is basically give us three categories. Okay, untyped choices. If we have the types, then it's going to be this, right? R times 2 plus 1. What is R? What is R? What is R? If our dependencies are not typed, that machine learning algorithm is going to give us three choices: left arc, right arc, or shift. But when they are typed, its choices are much larger. It is the cardinality of R times 2 plus 1. What is R? R is like a set. It looks like a set because it says the number of elements of R.
Relationship set, maybe?
Yes, it's the relationship set, dependency type set. So dependency type set times 2. Why is it 2? Because I have left arc and right arc, right? So what are the features that I'm going to use for my machine learning algorithm? Of course, the top of the stack word, and it is part of speech. Okay, first buffer in the word, part of speech. Second one, third one, etc. Okay, so this one is dependent on the word itself and it's part of speech too. Is it noun? Is it verb? Is it a proposition? And what is coming next after that? Okay, like that. There is no search involved, but some people say that why don't we try shifting and right arcing and left arcing at the same time, and we will form some kind of a search tree, and we will do this maybe for a few steps, and we will have a chance of comparing the results of these steps, and later we will come back and backtrack and we will pick the best one. It is a little bit slower, but we will keep not just a single tree, we will keep k good parse trees. So this will make more sense, and our machine learning algorithm later say that this is a better parse tree, this is the worst one. And sometimes using this, maybe we can find more than one parse tree for the same sentence. Okay, if you do include this search step. But the algorithm that I gave you does not include any search steps. Okay, so it provides a very fast linear time parsing with good performance. But actually there are many much better algorithms based on dynamic programming that produces much better results. But this one is simple and gives good enough results. That's why we looked at it. Okay, good. So what are this one, what is our features? What are our features? Features are like this. Let's say in my stack, I have my root. I have has. What is the part of speech of has? Okay, it is verb. Okay, and the present term. It is good and it is adjective. In my buffer, I have control and noun. Okay, with these features, and the words, my feature space is going to be very, very large. Why? Because if it's a one hot vector like this, what do I mean by one hot vector? If each word has a binary position in a 1 million dimensional vector, and if each word has another indicator for its part of speech tag, that will make a very large vector actually. Okay, that will make a very large vector, and my machine learning algorithm will have to work on these kind of vectors. And these are some of the examples of the stuff. S1 stack 1 word is good, and the stack 1 type is adjective. S2 word is has, S2's type is verb, and S1 stack 1 word is good, etc. So if these are met, this is a feature. If these are met, this is a feature. Okay. What does this mean? LC of S2 stack. What is TT type? Preposition. I don't know what this is, LC.
Can it be least common? Maybe.
Least what? Least common? No. What? I don't know. I don't know. Type is there. S2 word is okay. This is L. Oh, maybe the left connect. Okay. So if S2 is connected to somebody, okay, if S2 is connected to somebody, whatever I have am connected, left connection, the word is he, and its link type is N subject, and S2 word is has, so that means that it is connected to a word he, so that means that at the beginning of the sentence I have he has, something like that. So these are the connections. The verb of the connection, verb of the left connection, the type of the connection. Okay. Good. So these are the conventional feature representations, and our machine learning algorithm is going to use these features. So how would you measure your accuracy? How would you measure your performance if you are doing the dependency parsing? Okay. So usually you do number of correct dependencies over the number of dependencies. Okay. So this is the correct one. This one says that there is between 1 and 2, there is a connection, and it is subject. She saw the video lecture. Okay. Between 0 and 2, okay, between 0 and 2, there is a connection, and it is a root connection. So this is the gold, this is the parsed. It looks like this is okay. This one is okay too, right? This one, no. I mean, this is not, because between 3 and 4 it says, between 3 and 4. Okay, you understand this, right? Okay, let's draw what the parsed one says. Between 0, and I'm going to draw it with the red. Between 0 and 2 there is a arc. Between 1 and 2 there is an arc. Between 3 and 4, see, it makes a mistake because the dependency should be between the and lecture. Okay. Between 4 and 5 there is a arc, and between 5 and 2 there is an arc. 5 and 2, like that. It should be like the on the top, but it is coming back like that. Okay, so this one says that 4 out of 5 I found it. What is correct? 4 out of 5. 4 out of 5. It is untitled assignments, I guess. It says 1, 2 it knows, 2, 0 knows, 5, 2. Okay, so if you look at the arcs, they are fine. It find the arc here, it's okay. Arc there, it is okay. This one is okay, this one is okay, this one is okay. So 4 out of 5 arcs are found fine. But if you look at the types, only this one is okay. And this one is okay. The rest is gone. So this is how you measure it. The correct source and destination of the arcs and the types of the arcs. This is how I evaluate my dependency parsing results. Okay, good. Any questions so far? As I said before, even if it doesn't work right, you will never get any non-projective 3 assignments, dependency trees out of this algorithm. It will be always projective. Nobody is going to intersect with. No arcs will intersect with other arcs. Okay, so but we said that sometimes there should be intersections. However, we're going to assign it. However, we're going to do that. So these are some solutions. First one is don't do it, okay? Just say that I cannot handle the projections. Okay. The second one is use dependency formalism which only has projective representations. Okay. If you start with a context-free grammar, okay, and it will allow projective structures only. So that might be a solution, although it's restrictive. That might be a solution. The third one is, okay, do this thing, do the algorithm, write the algorithm, run it, and after the algorithm is run, you run a post processor. Okay, this post processor will go over your lengths, and it will say that, okay, I'm going to change this dependency with this one, and that might cause some non-projectivity. Okay, so and the fourth one is kind of an example for the third one. Extra transitions that can model at least most non-projective structures. Add an extra swap transition. Okay, this could be done after you are done with the algorithm. Or move to a parsing mechanism that does not use or require any constraint on projectivity. For example, the graph-based MST parser. Okay. So I think I am out of time, and that's the end of the dependency parser stuff. I will not talk about it. And this one is an example work from Manning, the owner of these slides. Their system uses a neural graph-based dependency parser. It's a graph-based parser. It is trying to form a minimum spanning tree. This MST means minimum spanning tree. What is minimum spanning tree?
What is tree that that is the most balanced, like informally.
No. A tree. Well, it's a tree
Sorry,
out of
sorry.
a graph.
That it has the shortest way from root to all the leaves. I
Okay,
think.
it is the tree out of a graph. Okay, it's a subset of a graph, like H subset, which is a tree with the cheapest total edge value. Okay, so this algorithm, it looks like you are assigning these numbers between the dependencies of this sentence. All kinds of dependencies like are possible, all of them. Okay, so you assign these numbers to these edges, and then you run your minimum spanning tree algorithm to find the minimum spanning tree out of this graph. And if you use a neural classifier or neural score assigner for the edges, you may end up with these kind of numbers. These are nice numbers, better than the others. Okay. It is slow. Why? Because it has to consider all possible dependencies. There are n squared possible dependencies between the words of the whole sentence. Okay, so I never showed you anything about any machine learning algorithms to make these decisions, but you may guess them how they work. So their feature space is known, and we could use any machine learning algorithm that you like. Okay, that's it for today. That's the end of the class. Next week we will have our midterm exam during the class time. The midterm exam will be 2 hours, and I will send you the instructions about the online midterm exam. And I expect you to have a computer with a camera and microphone and a good internet connection. And the instructions will be mailed out shortly. Okay, study hard, and I will see you next week.